So what we're going to look at now is we're going to look at shear flow. Now, shear flow is going to become pretty important as we look at things that are built up. Because in engineering, a lot of times we have things that are built up. We don't have an extruded box beam. We have 4 pieces of wood nailed together. Or maybe we have an I-beam that's made of wood where we've got a couple of different pieces of wood nailed together. Basically, and what do these fixtures do? These fasteners, they keep things from sliding relative to each other. Now, the important thing at that point is what we need to look at is, okay, well, let's see how much shear force do I have in that fastener or that nail or the rivet or whatever we have that's holding this entire thing together. And so what we're going to do is we're going to define a new quantity that we're going to call the shear flow. And what shear flow does is it measures the shear force per unit length of the beam. And we represent that with lowercase q. And so we'll define this as the shear flow. Why is it called shear flow? I'll show you in a minute. We're going to take a look at some thin-walled sections that the way the shear moves through the thin-walled section is kind of analogous to fluid flow. And so we've kind of got the same thing going on, and we'll see that a box structure and an I-beam are going to flow in 2 different ways. So to calculate out shear flow, it's much the same as calculating out what the horizontal shear stress is. In fact, the equation's almost the exact same. So we're going to look at, once again, the vertical shear force that's being seen by the beam at that time. We're going to divide that by the moment of inertia of the area. And then we've also got Q again. And so remember from the other ones, what is Q? Q is going to be y bar prime times A prime. This comes in critical when we're looking at forces on fasteners, because remember what we've talked about Q, that's kind of the area that is driving the amount of horizontal shear stress in an object. And for shear flow, that Q value is really what's going to be, that's going to be the area that's driving the force on the fastener. Okay, and so once again, you've like to box your equations. This one right here, the shear flow one's, that's important to box. It's a pretty simple equation. There's not much to it. Let's take a look at the shear flow itself. And so these are the way that they deal in a thin-walled shape. And also you'll see this is where I was talking about where it's flowing. So the shear is going to vary across the beam. In this case, this is a box beam. And so, but the shear is going to move much like it's water flowing. So in this case, it's all going to start right here on the top. It's not going to start at the edges because they're closed in. It's got to come from somewhere. And it's going to go from here, and it's just going to flow all the way until it meets back at the bottom. And it's just going to go down there just like water would, and it's going to be varying through there. And you can calculate out what that shear stress is at any point by taking your cut, and there's my area. This would be my A prime, and I find out what Y bar prime is, and I can calculate all that just like I've done with the other problems. Now let's see, we want to, and so for the box beam, and the reason this one's important because it's a closed-in shape, it's going to start at 0 at the top, at point A, and it's going to flow around. And it's going to be a smooth transition, and actually at the same Y value, the shear flow here and here, if that was a straight line, because I can't draw a straight line, but let's assume that's a straight line, the shear flow at those 2 points is going to be the exact same, because it's going to have the same, V is not going to change anywhere through here, I is not going to change anywhere through here. The only thing that's going to change is going to be that value of Q, and so at this point they'd have the same Y prime bar A prime that any other one would have. It's going to maximize at C, which is our neutral axis, just like with our horizontal shear stress. And then from there, it's going to slowly reduce till it comes back together at point E, where it's also going to be 0. And so the sense, remember when we talk about vectors and sense, it's all going to be deduced. That's direction. It's going to be deduced from where it's going. So as I'm pushing down from the top here, everything starts at the top and flows to the bottom. Because once again, think about it like a fluid flowing through things. If my shear force came this way, what would happen? Well, all of it would be starting here at E and then flowing to A. So it's going to flow in the direction of the vertical shear stress. Now let's look at an open section, because this one's a little bit different. And because it's an open section, it's not really, it can't start here because it's going to flow straight down and it can't flow out to the sides. So what it does is the shear flow starts at the edges and flows their way in. So you can see from this graph here, and we have two different shear flows that are coming together. So you've got shear flow 1 coming from A, shear flow 2 coming from A prime. When you get to the bottom here, what happens is they both add together. And since this is completely symmetrical, in the case of this beam, Q1 and Q2 are going to be the same, so that Q that's going down the middle is just going to be twice what it was coming out the sides. And then when you get to the bottom, it's going to split and go to E again. And once again, just like with the other one, except now we're not looking at the top and the bottom, there's no shear flow here because there's no area on this side causing any kind of shear stress. Once you get here, okay, well, what happens? Well, you can calculate out the shear flow, the shear stress here, because, well, here now you've got, there's my Q. And so I can calculate out, there's my Y bar prime. And from here, I got my area, and so then I can calculate out my Q. Now, the thing is, I'm sorry, I'm erasing all that. I mean, the thing is, this is the only area that's really causing that shear stress in that flange of the beam. Because it's not, the rest of the beam's not causing any of that shear stress, it's just that area there. So we're just looking at this little section of it too, and it's not the entire top of the beam. And so it varies, it comes together. Once again, it's still at the neutral axis. It's going to be maximum. Now, back when I was a student, one of the things that we did, and I hated having to do this because it didn't click the first time that I saw it, is on one of the exams, we had a bunch of different shapes that we had to plot out what the shear flow in the shape was. And that was just murder, and I didn't like it. I understand it a lot better now, but with time, you get really much better at this. But the big thing to remember is when you have a closed shape, like that box from above, when you apply the force to it, the shear is going to start in the middle, and it's just going to flow back to it. When you have an open shape like our I-beam, it's going to start at the ends and flow down. So if you have something like a triangle, okay, well, what happens? So if I apply a load to it, the shear is going to start here, and it's going to flow down. And so once again, if you think about it kind of like water, that's what's going to happen. So if you have like a U, ooh, you don't need to see all that. So if I have a U-beam, and I'm applying a vertical force here, what happens? Well, the shear is going to start here, and just like water, just like a fluid, it's going to flow all the way to the bottom and meet there. So basically, as long as you keep that in your mind, it's shear. The reason we're calling it shear flow, just think about it, it's like a fluid flowing. You can hopefully kind of start to see where it's going to flow to and where the forces are going to be. And then you're going to have to, the hardest thing with shear flow and any of this stuff is always going to be what? It's going to be calculating out Q, because it's a goofy thing to have to calculate out. But once you get that down, you should have no problems with any of these.